Recently in physics, we've been talking about describing kinematics. This is the how far, how fast, how long does it take for an object in motion. But now we want to move into talking about why. Why would an object move? Why would an object change what it's doing? Why would an object not change what it's doing? These questions are answered as we begin to talk about forces. So first, we want to describe a force. A force is simply a push or a pull. But the thing that the force can do is that it can give energy to an object, and this force will cause a change in the motion of the object. It's important to identify what our system is and talk about forces that are internal in the system or forces that are acting on the system from outside. These come from the environment. A force is also a vector, so we would represent it with an arrow. A force has a magnitude and a direction. In order for us to change the motion of an object, we simply want to push or pull, but we have to talk about what force is acting on what object. And this is where we're going to need some sort of a model to help us. So we'll draw diagrams just like we've done in the past where we're sketching maybe the velocity of something or its path, but now we're going to start describing the forces that are acting on an object. It's important that we understand that this is an interaction between objects. That means that you have to have one object either touching or influencing another object. So this is where we will label the forces that we are working with. So we have two different main types of forces that we could come across. Like I said, we could have objects that touch each other. These are called contact forces. And then we have forces that are long-range forces. A long-range force is simply a force that acts on something without actually touching it. For example, the Earth is currently pulling down on all of us, but we're not actually touching the center of the Earth. See, this force originates at Earth's center and it acts on our center. So we say that this force is acting on the center of mass of an object. Well, you're very far away from the center of Earth, and yet it can still pull on you. You could get further away from the center of Earth, even leave the surface of the Earth, but Earth's gravitational field is still doing work on you. So these long-range forces are going to be forces due to gravitational fields. If you've ever played with magnets and you can feel the force between these certain metals, that's a magnetic field. That would be another example of a long-range force. Or we could also have a force of electrical fields acting on each other. These would be another example of long-range forces. They don't touch the object, but they can still influence the behavior. So all forces have an agent. We consider an agent as a cause. So we say this is the force due to gravity. This is the force due to the push. Or this is the force due to tension in a rope. And so we give these agents a subscript and label them F with the subscript T or F with the subscript F for friction. So let's talk about what some of those forces would be. One of the big forces that we deal with frequently is that friction force. Friction is a force between objects that come in contact with each other, and its job is to oppose motion. So it's going to act against the motion of the object. For this reason, very often friction is considered a negative force because it acts in a negative direction from the motion of the object. We also have a force called a normal force. A normal force is simply a support force. It's something that opposes the weight of the object or the force being pulled down by holding it up. A normal force always acts perpendicular to the surface. So if you're on a floor, that's easy to see. But if you were on a hill skiing, then the normal force would be perpendicular to the hill. We can also have springs exert forces. If you've ever jumped on a trampoline, you're thankful for that spring force. But the spring force is what makes it fun because that is a restoring force. You stretch the spring and the spring wants to pull back, and that restoring force is what will eventually throw you back up in the air. That makes springs a lot of fun. Tension is another force. Tension is a force in a string or a rope or a belt that's exerted when you stretch something and pull it tight. Thrust is another force that we might deal with when we have some sort of a fluid pushing an object forward. So if you take up a balloon and you blow it up and then you let the balloon go and it like this, that's the force of air being pushed out the back, and that thrust force is the reaction force that's causing the balloon to move forward. Or a rocket can have a thrust force as it pushes gases out the bottom of the rocket. That reaction force recoils the rocket up into space. And weight is a force. And a lot of times we get weight and mass confused. Mass is how much matter I have, the number of atoms that make me up, and that doesn't change unless I get to eat lots of cheesecake. Of course, Miss Jenkins enjoys eating cheesecake. But weight is a force that happens when this long-range force of gravity pulls on the mass of an object, and it presses my feet into a scale, and that gives me a weight force. So, in order to study forces acting on an object, we're going to use a tool called a free body diagram. And a free body diagram is simply us drawing an object and labeling all of the forces that are acting on that object. So we will identify all of them. They could be contact forces or they could be long-range forces, but we're going to label them F with a little subscript for the agent that's causing that force. It's important when we draw a free body diagram that we say the object is simply a dot. We're going to represent that dot at the object's center of mass. So for us, that's about belly button height. So we would say, hey, you are uniquely and creatively and wonderfully made, but in physics, you're just a dot. So we'll represent you with the dot, and then we're going to start our arrows on the dot and move them away in the direction that that force is acting. So let's try it. Let's draw a free body diagram for a book that's resting on a desk. If I took this Chromebook and I had it resting in my hands, I would certainly first want to replace the book with a dot. So I would say, okay, here is my book. And then I want to say, what's acting on my book? Well, usually it's easiest for us to see that certainly the earth is pulling down on the book. So we draw an arrow pointing down, and this is a force of the earth on the book. Well, we say that this force is a gravitational force. It's the force due to the earth's mass. We're going to call it the force due to gravity, and we call it F subscript little g, the force due to the earth's gravity. Okay, it's important to get little g not confused with acceleration due to gravity. Acceleration is the action. If I were to actually drop the book, you would see it accelerate at a rate of 10 meters per second every second, approximately. But I don't want to get confused between acceleration and the force due to gravity. So this force is what's going to cause the acceleration. That's the why. Well, what else is acting on the book? Well, we can see gravity pushing it down. We can also see that my hands are holding it up. They're providing a support force. That's the normal force. So we would draw that force upward and label it F with a subscript N for normal. Because this object is not accelerating downward or upward, it's important that I draw these two vectors about the same size. If I added them up, this up force would be considered a positive force. This down force would actually be considered a negative force. And this one plus this one should give me 0 net force. Well, what about if you had a child that was just sitting on a swing? You know, if you had a kid sitting on a swing, swinging back and forth. How do we represent this? Well, we once again make the child a dot. And we say, what is acting on the child? Well, certainly the Earth's gravity is pulling the child down. So we would have a downward force, F subscript G, the force due to gravity acting on this child. And then we have something holding the child up. In this case, it's not really a normal force holding it up. We have some strings or ropes or chains holding the swing up. So we're not going to draw two arrows to represent those. We're going to kind of combine them into one. But if this is rope holding the swing, then this up force would be the force of the ropes. We would say that's a tension force. It's possible that we could have like a tire swing where there was just one rope. If I wanted to draw two, if that bothered me, if I wanted to draw two, then I would want them to be shorter, but the same. But these two should add up to this one. Like that. Well, you could do that. It's not inappropriate. It's okay. But if our child is sitting on a swing and all of a sudden one of these strings breaks, now what's acting on the child? Well, Earth is still pulling down on the child, but what's holding the child up and now? That's right, nothing. So in this case, there would be nothing up. And this child, we could expect to fall down. What if you had a ball and you just hold a ball in your hand? How would we draw a free body diagram for a ball being held in the hand? Well, we draw the ball. Can I make this be a ball? Sure. What's holding the ball up? Well, I don't want to say it's the force of the hand, because then I'm going to get into so many subscripts that I'm going to have to explain. But this hand is supporting the ball. So this is just going to be a normal force again. So I would just draw this Fn. And yet, what if you took something and you wanted to push it across a table? How would we draw a free body diagram for a plate being pushed across a table? Well, this is where it gets a little tricky. We might need a little more information. So let's assume that we have an object that we're pushing across a table at constant speed. But if you've ever pushed something across a table, you might hear it slide. That doesn't slide very well, but you can hear it move across the table. That sound that you're hearing, that's friction. So we have some more forces. We certainly have the plate. We have the Earth pulling down on the plate, the force due to gravity. We have the table holding the plate up. That's a normal force. F normal. And even if I had a plate and I pushed it across in chair, there, you can hear that. I'm applying a force this way. This is called an applied force. Any push or pull, it's just me touching that object and applying a force, Fa. But as it went across, you could hear it kind of sliding on the floor there was some friction, FF. My friction force is acting against the motion of the object, so I'm going to make it be negative. My applied force is causing this motion. Now, you might have noticed earlier when we talked about when the down force was equal to the up force, it made the object not accelerate. The same thing is true of the left forces equaling the right forces. If these two forces are equal to each other, then the object will not accelerate. We got to be really careful. That doesn't mean the object won't move. You can move and not be accelerating, right? We've talked about how that is moving at constant velocity. So in this case, our object can move at constant velocity, and if I pull it this way, I have an applied force this way, there's a friction force that way, and it's still moving at constant velocity, then I know these two forces are equal in magnitude, but opposite in direction. If I wanted to accelerate this, well, then one force would have to be bigger than the other force. And I'm going to accelerate in the direction of the net force, the bigger force. So, when we talk about forces, we end up talking about Newton's laws. And these are laws that probably you could repeat or fill in if I got you started on them. Right? And you've heard of these laws, but what we want to do is kind of zoom in and take a closer look at them. So Newton's first law of motion talks about an object at rest tends to stay at rest, and an object that's moving tends to want to keep moving in a straight line at constant speed. This is sometimes called the law of inertia. Inertia is the tendency of an object to not want to change what it's doing. It wants to resist changes in its motion. Whatever it was doing before, it wants to just keep on doing that. So if it was at rest, it wants to stay at rest. If it was moving, it wants to keep moving at constant velocity, no acceleration. Okay? So this says that an object stays at rest or it stays in motion unless acted upon by an external force. What we mean is there has to be, if we add up all of the forces that are acting on them, it has to be more than zero. There must be a net force. So we sometimes refer to Newton's first law of motion as a law that describes when forces are balanced or objects are in equilibrium. Newton's second law of motion is one that we have an equation for. He studied forces that were acting on an object, and he tried to minimize gravity or friction by reducing some of those forces. Maybe sense something on a horizontal air table, or roll something down a hill to try to make things happen at a slower pace so he could still study them. But remember, a force gives energy to an object, and that energy can cause a change in an object. Well, change is a 50-cent word for acceleration. So a force causes an acceleration. And this way, if you apply a greater force, you're going to have a greater acceleration. So force and acceleration are directly proportional to each other. When we say acceleration is directly proportional to the net force, the net is the sum of all of the forces that are acting on the object. So if we went back to our plate example, if we add this force, up forces and down forces, we would get zero. If we added left forces and right forces, we would get zero. So the net force acting on my plate is 0 newtons. This means my plate is going to keep doing whatever it was doing before. So if it's moving, it's going to keep moving at constant velocity, but if it's at rest, it's going to stay at rest. Well, what if I want this to accelerate? Then I need to apply a net force. I either need to reduce the friction, make there be less. Now I have a net force. My object is going to move in the direction of the net force. If I add the left forces with the right forces, I'm going to move to the right. My up and down are still 0. Okay? But what about mass? We talked about inertia. Inertia is related to mass. If something has more inertia, it must have more tendency to keep on doing what it was doing before. means it really wants to resist changes in its motion. So it's very easy for me to take a small ball and, or a marble or something, shake it back and forth, or move it around a little easy. It doesn't have very much inertia. It's easy for me to change. But if instead I had a bowling ball, that's harder for me to shake back and forth. It has more inertia. It wants to keep doing whatever it was doing before. Well, mass is inversely proportional to acceleration. If you have more mass, then you're going to give the same force to two objects. What happens to the acceleration? Well, if I give a force to this little bitty mouse, it goes whee across the board and accelerates really easy. But if I give the same force to a much bigger mouse, it's like whee, and it doesn't accelerate very much. So forces are vectors, and we want to add multiple vectors, just the same way that we've been drawing velocity vectors and those things. We have to move them tail to head. We've got to label them. We've got to add them. So we draw a resultant after we've laid those out. That resultant, instead of calling it a resultant, now we have a net force. That resultant is the sum of these forces. So if we have multiple forces, if I had force 1 horizontally and force 2 vertically, I would pick up force 2 and slide it out over here and put its tail at the head of force 1, so it's going out and then down. My resultant force would be the red arrow. That is the net force on the object. It's the sum, the vector sum of all of the forces that are acting on the object. You will see net force written two different ways. You might see it as F-N-E-T. That's net force. This is the sum of the forces. But you might also see it as sigma F. The Greek letter sigma means the sum of the forces. So both of these things mean the same thing. And I want you to get used to being able to see them both and recognize them both that way. So if we put this idea that acceleration is directly proportional force and acceleration is inversely proportional to mass, if we put these two things together with our net forces, we get the equation for Newton's second law. And it says that the acceleration of an object is equal to the net force divided by the mass. This is Newton's second law. Or we might rewrite it and say net force equals mass times acceleration. You can see this in both ways. But now notice that we have brought about mass as part of the important piece of the puzzle. Okay? We've not dealt with mass when we've been studying accelerations or velocities or how long it takes something to fall. Now mass is going to be part of our equation. So when you go about problem solving, as you come across using Newton's laws of motion, you first wanted to figure out what forces are acting on the object. We want to draw a free body diagram, label all the forces, add your forces up to find the net force acting on the object, use Newton's second law to calculate acceleration, net force equals mass times acceleration. So acceleration would be net force divided by mass. And then if you have the acceleration of an object and you wanted to know how fast it will be going in 2.5 seconds later, well then we could use kinematics and find that final velocity. Or we could find how much time it will take it to go somewhere else. Or we could find its final position. We say, what does an unbalanced force do to an object? An unbalanced force will always cause a change in an object. So let's kind of take a look at some of the units that we'll be dealing with when we talk about Newton's laws. 1 unit of force causes a 1 kilogram mass to accelerate at 1 meter per second squared. So the unit of force is a derived unit. That means it comes from the units of mass and the units of acceleration. So we say force is mass times acceleration. The unit of mass is kilograms. So So if we take 1 kilogram, if you get something in grams, you have to convert to kilograms. If we take a 1 kilogram mass, we accelerate it at 1 meter per second squared, then we get 1 Newton. A Newton then is a kilogram meter per second per second. Like I said, it's a derived unit. So let's try to practice a little problem here. And I want you to do this on your paper. 2 horizontal forces, one of them is 225 newtons and one of them is 165 newtons. And these are exerted in opposite directions on a crate that has a mass of 5 kilograms. What is the net horizontal force on the crate? What is the net vertical force on the crate? And what is the acceleration of the crate? So first, you have a problem with some forces. We want to draw a free body diagram. So on your paper, draw a dot that represents the crate. List the things that you know. Okay, well, I know that the mass of this crate is 5 kilograms. I know that I have 2 forces. One's 225 newtons, and this is horizontal, so I'm just going to draw 225 newtons. And the other one is in the opposite direction, and it's less. I want to make sure that I draw it shorter. So this one is 165 newtons in the opposite direction. Well, what do we know about these vectors? Well, I need to know that this is a negative force. So I'm going to put it up here as a negative 165 newtons. That means it's 165 newtons, from my perspective, to the left. Okay? So they say, what is the net horizontal force on the crate? To find that, I add the forces. So F net is going to be 225 newtons plus negative 165 newtons. Okay, that will give me the net force on the crate. And then they said, what is the net vertical force on the crate? Uh-oh, I didn't draw vertical forces. Are there vertical forces acting on my crate? Absolutely. Well, what are those forces? Well, I would have a force of the earth pulling down on the crate. That's the force due to gravity, F subscript G. And I would have a force holding the crate up from the floor, F subscript N. So these 2 forces add together. If my force is staying if my crate staying on the floor, I know that the net force here is 0. If the up force was bigger than the down force, my crate would all of a sudden start accelerating up off the floor. Or if the down force was bigger than the up force, well, it would start moving down through the floor and accelerating. So since it's just sitting on the floor, I know these 2 are equal and opposite. All right, and it wants to know, what is the acceleration of the crate? Remember, acceleration is net force divided by mass. So if we have 225 newtons to the right and 165 newtons to the left, our net force acting on this crate is 225 minus 165. Well, that's 60 newtons. And we want to divide by the mass, which is 5 kilograms. And 60 divided by 5 is 12. And so we get A is 12 newtons per kilogram. Wait a minute, Ms. Jenkins. We haven't been talking about acceleration as newtons per kilogram. We've been talking about it as meters per second squared. You're absolutely right. But remember what a newton is? A newton is a kilogram meter per second per second. And if I take that and divide by kilograms, this is going to go away, and I am only left with meters per second squared. So really our acceleration is okay. It's 12 meters per second per second. Very nice. When we apply Newton's second law to objects, in all objects having mass, we considered that if I took a banana and a gorilla and I dropped them, would they accelerate at the same rate? And Galileo hypothesized that yes, this would happen. That these two objects would hit the ground at the same time, not with the same force, but with a force that's proportional to their mass. But they would all have the same acceleration. And we did a lab where we dropped different things that had different masses, and we found that to be true as well. So when a mass gets accelerated, it's being pulled down by Earth's gravity. This is what causes weight. So we can say that from F equals mass times acceleration, we can take an object's mass and multiply it by the acceleration due to gravity. This specific one, Fg is, this specific gravity is negative 10 meters per second per second. This force is the force due to gravity. This is what we call our weight. Weight is a force. Our weight is measured in newtons, not pounds and not kilograms. Our weight is measured in newtons. Now, if you think about it, I don't really want to know what my weight is in newtons because that's going to keep me from eating another piece of cheesecake. But I don't mind knowing what my mass is in kilograms. My mass in kilograms, since we're dealing with the English system, my mass in kilograms is roughly half of what my mass is in pounds. Well, I don't mind knowing that because that will allow me to eat another piece of cheesecake. So this last problem that we have here is a problem that we can work through. Now this is an up and down problem, and it asks us to find a tension in a rope and wonder if the tension in the rope is going to break or not. So we have a bucket that's being lifted up a certain distance, and this rope is advertised not to break if the tension is 500 newtons or less. And this bucket is not lifted at a constant speed, which means the tension in the rope is not going to stay constant. The net force is not going to stay constant. We're going to end up increasing the velocity of the bucket, and this is going to accelerate. Because of this tension is going to kind of change progressively, and we want to know, well, is that rope going to be able to do the job or not? So to do this, we want to draw a picture, draw a free body diagram, label everything that we know. Our free body diagram would be the mass of the bucket. It is 50 kilograms. We know we're going to lift this up with some tension force, but we don't know what this is. But we also do know that the bucket has a weight, Fg. And we can find this. We just found that the bucket's weight is its mass times gravity, right? So 50 times negative 10, well, I'm already sitting at negative 500 newtons, okay? But in order to try to accelerate this up, we want to use a strategy of finding the net force, which is the sum of these vectors, and then solving for acceleration. So remember, net force is going to be the sum of the vectors. So it's the tension force plus the gravity force, but this is negative, so I have to subtract this, right? But I also know that the net force will always cause a mass to accelerate. So if I'm trying to figure out what this is, I have two equations. I can plug in MA for net force, and I can plug in mg for Fg, and I'll rearrange to solve for Ft. And I end up getting that Ft is going to be Ma plus mg. You can factor mass out of this, and you can get Ft is mass times A plus G. Well, we know what G is. We're having to fight against gravity. It's going to be 10 meters per second per second. What about the acceleration? If you start the bucket at rest, and it ends up going at 3 meters per second over a distance of 3 meters, I didn't have time anywhere in the equation, so I might want to use the v squared equation to solve for the acceleration. If I do that, I get acceleration to be v squared over 2 times the height, and that gives me an acceleration of 1.5 meters per second squared. Well, if I come back in here and I do mass times 1.5 plus mass times 10, then I'm going to end up with about 570 newtons of tension force. If this is only claimed to hold 500 newtons, then yes, this is in danger of breaking. That could be a problem for me.